prove on magnitude and direction of acceleration of a particle undergoing uniform circular motion. We know that a particle is in circular motion if it travels in a circular path or arc at constant or uniform speed. This is the center, and the velocity we have seen is tangential. So at this point it will be tangential, so that the acceleration will be center seeking. We call it centripetal acceleration. At this point it will go this way, and it is also center seeking. So in order to prove that, let me draw a clearer diagram, so to speak. Let's assume that this passes through the center and this is axial. So let's assume that the particle is at this point P. So tangentially the velocity will go this way, tangentially. Let's draw a perpendicular at this side, so that the acceleration is seeking the center. So we can name this angle of the velocity to the vertical as theta, so that here is also theta. We know the rule in triangles. So let's assume that here is x on the x-axis, and from here where the particle is to here is y. Let's assume that it is y. So we have a triangle that looks like this, xy. Then the particle is at this point P. So we can now, like I told you, here is theta. So the position vector of that particle will be r is xi plus yj, if you remember our topic on the vector. So it means that the velocity will be equal to the r over dt, which is the x over dt I hat plus dy over dt j hat. So that if we just substitute from here, you see that the velocity component, this is v, the velocity component v can be vx or vy, if we use here to coincide with the straight line that we have drawn parallel to the one passing through the center O. So that we now have that v also is equal to vxi plus vyj plus vyj. And this velocity component, you see, is for here minus v sine theta, because this forms a triangle, minus v sine theta, because it's parallel to this side is parallel to this side. So the vy here is adjacent to this angle, so it's adjacent to this angle, so it's v cos theta, This one is j and this one is I hat. We know that acceleration will give us dv over dt. For instance, we have d dt of this sine theta. This sine theta that we are seeing here, this sine theta is the same thing here as y over y, opposite over hypotenuse. This place is r, the radius r, so it's opposite over hypotenuse, adjacent over hypotenuse, cos. So it is minus v into for this y over r I plus v into x adjacent over hypotenuse, cos theta is adjacent over hypotenuse, x over r j. So that if we multiply through, we see that we have something like this: v minus v over r dy over dt I plus v over r dx over dt j. So you know that we have said that the rate equal to minus v over r into vy, if you like, I plus v over r into, this one is vx j. But we have seen that v dy dt is equal to v cos theta, while the x dt is v sin theta. So if we put it, we see that we have minus v over r into dy dt is v cos theta I plus v over r. The other one is v minus v sin theta j. So that we have it to be equal to minus v squared over r cos theta I plus minus v over r squared sin theta j. So this is the component, acceleration component for the x and y axis, acceleration component of the x and y axis. So in order to find the magnitude of this, you know how to find the magnitude. A vector is equal to square root of ax squared plus ay squared. So if we do that, we will have square root of this squared is v squared over r all squared. Then is here, so we can factor it out. Cos squared theta plus sin squared theta and this thing here is equal to 1. So square root of v squared all squared is just equal to v squared over r, and we have proven it. And that centripetal acceleration also has component p. It has component. This one is moving to the x direction, and this one is going down, ay. This is a, and remember that this angle is theta. Remember that angle is theta, which means that this implies that tan theta is equal to ay over ax. Or if we have used this first one, if we have used this one for theta, we see that it's equal to vy over vx. Remember also that this particle, the time for it to move from this point P and back to that point P, called the period. The time to cover one complete cycle is the period of oscillation, and the distance moved is just the circumference of the circle I r, and the time is equal to period for it to cover that distance. That means if we use v is equal to distance or displacement over time, so we have that now time, which is for here now period, is equal to 2 pi r over v, because this one will come here, the other one will go there. So that is how to do this type of problem. So we have shown that a is equal to v squared over r. Remember, we have been quoting this thing from high school, but now we have seen how to get this. So thanks. Click on the notification button so that whenever we post new videos, you will see them. Ciao. Have a nice day.